Той идва за трети път в България и все на OpenFest. В момента интересните неща, с които се занимава, са точно свързани с радио. И миналата година на протестите ползвахме даже част от неговия софтуер за едно много интересно тулче, което Васил показва в InitLab. Един TV приемник, който изглежда като това USB е там, което си е забил Harald. И го ползвахме да подслушваме полицията. Те идват насам, ние в другата посока. Той ще ви покаже как може да правите подобни неща. Надявам се, няма нужда вече да го представям, но все пак ще кажа, че той се занимава с GSM технологии от много време и неговата идея, принцип е да се направи свободна имплементация на GSM протоколите, така че всеки да може да направи security анализ на тези протоколи, което в момента малко не е много лесно. И така, so Harald, the floor is yours.
Okay, well, thanks. Whatever Marian just said is probably wrong, but okay. Welcome everyone to this presentation about RTL SDR, which is well, a very, very, very cheap way to get involved with software-defined radio. Just for me to have a little bit of an idea about what to expect in terms of the audience, how many of you know what SDR is, what software-defined radio is? Okay, that's already a quite large amount. Okay, so then I'll go as quick as possible through the various slides. Basically, the big difference between traditional radio and software-defined radio is, well, if you look at traditional radio, you have a hardware-based receiver and a hardware-based demodulator for the specific modulation that you're using, like an AM modulation or an FM modulation in analog radio. Also, it means you have analog fixed filters that have certain bandwidth for the specific standard or a radio system that you want to implement. You receive the signal analog or you digitize after basically you have done a complete analog demodulation path. So it didn't really change all that much in the 100 years of history that we have in terms of radio technology. So if you look at FM broadcasting or something, if you ignore the stereo aspect of it, it's actually very, very, very basic technology. Or if you even go further back to AM, it's like technology of our great-grandfathers, but not really today's technology. Now, with software-defined radio, basically you move more digital aspects into the signal processing, and you do more of the things that you used to do in hardware, you do that in software. So you still have, of course, some kind of tuner, some device that actually is able to receive the data or the radio signal that you want to receive. And then basically either you have what's called a 0IF down conversion architecture, where you take the digital signal. Let's say you're interested in a signal at 1 gigahertz, then you tune your receiver to 1 gigahertz, and it gives you a chunk of a certain bandwidth, let's say 2 megahertz of bandwidth. It cuts that chunk out of the spectrum at 1 gigahertz. It shifts it down to baseband, so basically to 0 hertz. And then you have the signal, what we call in baseband, and it's a direct conversion, as said, so-called 0IF, or no intermediate frequency down conversion. The other idea is to convert not to a 0IF, but to a very low intermediate frequency, and then sample that intermediate frequency and work with the samples on that. Whereas in the 0IF, you convert to baseband, and then you sample the baseband data with an analog digital converter. And the ADC can never be fast enough, and it can never have enough resolution. So you want to have as much resolution and as many bits as you can get, and as high of a sample rate that you can get. And then all the things, or most of the things that you used to do in the analog sphere by building filters and all kinds of analog radio components, you can do that in the digital domain. So you use signal processing mathematics to basically implement the same thing or better ways of doing what analog radio used to do before. So what kind of advantages does this bring to us? Well, we have lots of flexibility, and that's of course very interesting, especially in a research context or in a well, experimentation context of any sort, that you don't have to build one specific radio receiver, and that's for FM radio, and you basically stop there, you build another one, and that's for AM broadcast radio, and you stop there, and you build yet another one that's for analog TV reception, and you stop, and you do the same again for each and every radio system that you want to implement or that you want to play with. So you get a lot of flexibility because you don't have things hardwired in analog hardware by selecting components, but you can do that in the digital domain, in software domain. So the only restrictions that you basically have is that the input frequency of your tuner must match the signal that you want to receive. So clearly a tuner that cannot go up to 2.4 gigahertz, you cannot receive 2.4 gigahertz with that tuner. The sampling rate must be wide enough that you can capture your signal. So if the signal has, whatever, 1 megahertz bandwidth, you need at least that bandwidth in your receiver and the corresponding sampling rate. Of course, you need the computing power to do that. Yeah, so all of the different radio systems you can actually implement in software, and you don't have to use your soldering skills and your electrical engineering skills or rely on other skills to do that. So that's used, software-defined radio in this flexible mode is mostly used in military and commercial infrastructure equipment. So in the military context, they always speak of waveforms, and you can download a new waveform into the radio. By this, they mean basically you have a new modulation or whatever scheme, a new communication system, and you download software into the radio so it can actually process this new standard or this new protocol for communication. And in telecommunications infrastructure equipment, also this flexibility aspect is used a lot. So today, when you buy, as a mobile operator, when you buy a high-end base station, it's basically a massive parallel computing device with a very advanced radio head, is what they call it, for the radio interface. And then it's all software, and the software decides whether you run LTE or you run UMTS or you run GSM, and how many carriers you run and at which frequency you run them. That's all software and done in software-defined radio. So in those applications, this flexibility is used a lot. In various other implementations, we still see SDR technology, but not in this flexible mode. So actually, a lot of the consumer devices that you can see implement concepts of software-defined radio. So if you look at a GSM receiver in your phone, or if you look at a Wi-Fi chipset or something like that, today they're quite a lot in the area, in the sphere of software-defined radio, but how can I say, the information how to program that radio and the tools and the specification and so on, the manufacturer doesn't release. So basically, yes, you have this generic radio device, but the manufacturer ships it with a firmware that's specifically for Wi-Fi only or for something like that. And you don't have the information, or often also not the tools to actually do anything else with those devices, because it's in some DSP ROM, or if even it's hardwired logic inside the receivers. So they use SDR technology, but they have removed the flexibility from that. And that's sort of sad. Well, there is some hardware that is marketed as SDR that existed for quite some time, for many years. The most common known device family for software-defined radio receivers that anyone could buy. Basically, well, there's the military stuff, which is way too expensive for any normal person to afford. And well, then there's the USRP family of Etus, which is a series of boards that sort of are in the range of, let's say, $700 to $2,000, which is still a lot of money. But well, it's in reach of a lot of people. And now in the last, let's say, 3-4 years, we see even lower cost devices. There's a device called the Funcube Dongle Pro or Osmo SDR, or now RTL SDR, which basically have driven the entry cost for people to experiment with SDR quite lower. So just very quickly, so you see it once, this is a slide of the original USRB circuit board. It's basically a large board on the bottom, and there's an FPGA in the center. You have ADC and DAC converters left and right, and then the boards which are stacked on top are the actual radio interface board, the so-called daughter boards. And then you have these SMA connectors where you can connect your antennas, and a USB socket where you connect your PC. That's basically how a lot of SDR community was able, in the open source world, was able to get started based on the USRP. I'm going to skip the technical details and go to another device which came up 4 years ago, which is the Funcube Dongle Pro, which is an interesting device since also price-wise it's already quite a lot lower than the USRP. However, it's limited to a very narrow frequency band or bandwidth. So it has this 96 kilohertz maximum sample rate, which is fine if you're an amateur radio enthusiast and you want to basically now receive your narrowband FM or narrowband AM or SSB radio from your amateur radio friends. You can also use it for systems like Tetra, which is a digital trunked radio system. Not sure how many in here have heard of Tetra before? Okay, well, some, okay. So that's a narrowband system that can fit within that. So with the Funcube dongle, you can actually do that. But most more modern communication systems you cannot receive with this device because it's too restricted in bandwidth. And the hardware design, the firmware are proprietary, which of course makes it less interesting for open source enthusiasts. So that's a picture of that device. It's a USB device that you can plug inside and you can connect an antenna. Okay, so that's basically, yeah, I'm going to skip some more slides about GNU Radio and so on, and get to finally to the RTL SDR, which is the main topic of this presentation. So what happened is that I actually don't know at which point in time. I would also guess around 2009, 2010. Realtek, probably everyone has heard that name before, is a Taiwanese manufacturer of all kinds of silicon. Starts from Ethernet chips. That's what most people know them for. But they also do all kinds of other chips. And what they built is a device called, or a chip called RTL 2832U, which is a single chip receiver for digital TV, digital broadcast TV. So they built this chip with the intention of enabling people to build small USB dongles which you can use to receive digital TV, like DVB-T broadcasts, which are basically, well, at least all over Europe and in other regions now, the common form of broadcasting terrestrial television. So this chip normally integrates the entire receiver and the demodulation for the respective digital TV standard, and all you get is an MPEG-2 transport stream over USB into your PC. So it's basically one of these devices where, okay, interesting, it has a lot of SDR components, but they implement all the receiver for me, and I only get to watch digital TV. And I mean, digital TV is boring. TV is boring in general. If you can receive all kinds of other things, why on earth would you want to receive TV? But still, manufacturers build those chips, since apparently some people want to watch TV. And yeah, so interestingly, now with this particular device, while Realtek also released a GPL licensed Linux kernel driver, which is already quite advanced for silicon manufacturers, that they actually release open source drivers. And well, you can watch TV. Okay, fine. They also released a limited manual to the video for Linux developers, but not much exciting in that manual. So this is how one of these devices looks like. So you can have a look meanwhile while I continue talking. So this, what you see here on the left-hand side is the actual tuner chip. That's not the Realtek device. This is just a tuner that down converts your signal from the radio frequency to low IF or zero IF, and then you see the traces here. This is basically the INQ baseband or low IF signal, and here you have your Realtek chip, which connects to USB, and what you see on top here is an infrared receiver, because people like to use remote controls when watching TV, apparently. I've been told so. So, okay, it's a TV receiver, but what's so fancy about it? Well, some people started to find out that on Windows systems, some of the drivers can also receive DAB, the digital audio broadcasting. And that was surprising, because the entire hardware manual doesn't say anything about DAB. And it turns out that Realtek put a special mode in this chip that allows you to deactivate all of the TV receiver and instead send the raw samples of the ADC over USB into the PC. And then you can implement your receiver and software on the PC. So what some of the vendors who built these USB sticks did actually is they activated that mode, and then you get the raw samples of the baseband into the PC, and in the Windows software, they implemented a DAB receiver for digital audio broadcasting. And then some people well, basically figured that out, and they started to do protocol tracing on the USB to find out how on earth this chip can get set in this special mode so it sends the raw samples over into the PC. Now, after some protocol tracing, this basically was figured out, and a project called RTL SDR was created, which is an open source project that basically talks to this Realtek chip. It activates this special mode for forwarding all the raw samples, and it consumes those samples and makes them available to various applications that may be interested in those samples. So basically, if you put those things together, the open source software and one of these cheap receivers, you have a very powerful radio receiver, and you can use any of the SDR that is commonly available in open source, particularly anything that's based around the GNU Radio framework, because GNU Radio is basically RTL SDR integrates as a so-called source, so you can take samples out of the receiver, you can feed them into GNU Radio, and then you can do whatever receivers are there. Now, the question maybe that many people have, okay, that's nice, but what kind of radio can I receive? What is this all about? Well, basically, there's a lot of radio around in the air. Here in this room, for example, we're using wireless microphones. Okay, well, you can hear me by your ears. You don't need a 20 euro USB receiver and a laptop for that. But what about somebody speaking in the next room? What about PMR systems, so the professional mobile radio used by security companies or police or airport security, for example. They're all interesting things that are happening on radio that you can tune in. Then, for example, there is AIS, which is an automatic identification system for vessels, for ships. Using that, receiving that, you can basically get every 3 minutes an update from every ship that's in the reach of your receiver, and you can basically track vessels as they move on the ocean or on rivers. There is ADS-B, which is a transponder system for aircraft. So with an ADS-B receiver and decoder, you can basically plot the current location with second accuracy of all the planes that are in the area, because all the planes are mandated to have such transponders built in. So there are many, many interesting signals. For example, also public transport companies in Berlin with Osmocom Tetra, which is a software implementing the Tetra radio system and the RTL SDR, you can listen into the traffic of the subway, the metro. So there are many, many interesting signals out there that you can explore and can investigate and learn a lot about signal processing in the meanwhile. This is an even smaller device from Hama, which is also using the same Realtek and a tuner next to it. Yeah, there's a variety of these different companies that manufacture those devices. One word about tuners. So the only difference between all those different dongles is basically what kind of mechanical size is used and what kind of antenna connector they use, and what kind of tuner, oops, sorry for that, what kind of tuner is, where are we? this slide. So which kind of tuner is used in the device? Because it's always the Realtek chip plus some tuner. Unfortunately, the best tuner, best in a sense that it covers the widest frequency range, is no longer available because the company went out of business that produced it. So the Elonix E4000, if you find one of those still, you can be lucky. Normally now there are different tuners in those devices, and the frequency range of what you can tune into is slightly less. If you look on the RTL SDR website, all the different tuners are compared, and you can get low-level details about this. Okay, before I talk more about interesting things you can do, let's just have a quick look at what basically is coming out of the receiver here right now. So I've tuned to a frequency, well, 99-something megahertz. That's broadcast FM radio. And what you see here basically on the top section is a spectrum plot of the signal that you receive. And we see at least 2 radio carriers here. And the waterfall diagram at the bottom is basically the spectrum plot on the top, but with the time axis associated to it. So you can basically see how the signal changes over time. You can, this is GQRX, is a free software program for software-defined radio, primarily intended for analog radio signals that you can pick up. And I can change the frequency by, for example, yeah, that's some radio station that we can pick up here. But, you know, analog FM radio, of course, is not very exciting. It's a little bit, I think we cannot increase the volume, unfortunately. Or maybe if I... Okay, so we can increase the volume. Let me reduce it again. So one of the things we can tune in, or try if we can tune into, is the microphones that we use here.
Хора си инсталираха това разширение. Просто...
Yeah. So whatever that was.
Probably the other room.
Huh?
Yeah,
the other room, most likely, yeah. So there's another one that's at 553, 850. That's probably this guy over here, or that one. It's probably too weak to receive here. I have a very bad antenna. Sir? The volume, yeah, I will, but it's too noisy at the moment, so I'm... Yeah, okay. Yeah, that's not strong enough here. But in any case, so you can basically look at different signals here. And this is just analog radio, so it's pretty boring because, well, you can buy a scanner receiver at your favorite electronics shop and you can basically tune the right frequency and hear the same thing. What's more interesting is if you look at digital signals, the digital information. But let me just quickly... Sorry?
We have an intercom, which is 746.150 megahertz.
746, oh, that's, sorry, 746.150.
Четвърта камера може да приближиш малко. Трета фокус.
Yeah, okay, so you can see, you can have fun with those microphones, but those are, of course, easy. Now what I want to show is basically some other stuff. If we just look at, I mean, of course we cannot hear the actual phone calls, but I'm just going to have a look at the GSM spectrum and see if we can find a GSM channel here in the room. No. Okay, probably too weak reception in here. No, it's the base station. At the downlink, you should always see something from, well, I need to reduce the wavelength of the antenna. But yeah, okay, that was just a guess. In any case, I mean this tool. This is called GQRX. Is an open source program for exploring radio waves, particularly for analog signals. I'm going to remove that noise again. Now, one other thing that we can try, as that I have no clue how good the reception is in here. In the hotel where I was yesterday, I got a lot of interesting signals. So let me just open a terminal. And there's one tool that's included in the RTL SDR. And that's called RTL ADSB. Yeah, and we actually receive some. So what you see here is one line prints that, the display is cutting the first characters, but you see these hex digits coming out here. Each of them is a transponder response of an airplane that's somewhere in the vicinity. Now, of course, this hex dump doesn't tell you much. I don't have a setup here ready to actually visualize that, but there's several software packages where you can basically use that data and plot it on a map, because it includes the GPS position of the airplane and the airplane registration number and so on. And even inside this room here with a very cheap antenna, we still receive those transponder messages, and not too few of them, as you can see. And the same is for this AIS system, for the ship, the vessel identification systems. You can have a look at those things. And as I said, there are many other projects that implement various different radio systems. So a small overview is here. There is for POCSAC pagers. This is a paging system that's used in some countries still. Of course, we have the QGRX, which is what I've just shown. There is all kinds of graphical interfaces like Qt Radio or SDR hash. There are many different implementations. One of them is the Tetra D-mode, which helps you to look at protocol traces of these terrestrial trunked radio systems, which are used by police and other agencies in various countries. Yeah, look at the traffic, have fun with it, and explore what's out there to explore. That's and I think I said for $20 US, it's a very cheap item for your hobby. So yeah, that was about what I wanted to show. We can of course try some other things. I can quickly see if I can find an online decoder for the ADSB, so we can copy and paste those hex strings and see if we get some more information about that. But otherwise, I'm happy to for suggestions to you what we should try, or what you want to know about RTL SDR. 123.7. Okay, we can do that. I just need to figure out where did I put the window with the GQRX, but probably I stopped it. No, it's still there, but where is it? It's analog? Yeah, no, so the signal, yes, of course. It's just I'm missing my software that I started. Yeah, this one is still running. That's why I cannot start the other one. So we're still picking up these signals. We can just look into decoding in a second. So use a local bin GQRX. Okay. There it is. Okay, so you said 1, 2, 3, 7. So let's see what we can. Nothing right now. Sorry? 1, 2, 4, 7, 5. 0.5. Yeah, not too much activity right now, apparently. Ah, there's something, whatever that is. Yeah, okay. So, yeah, okay. Anything you want me to check? 117.5. No, nothing there. Well, it's in here. It's not the signal level is not probably not so good. Let me disable that and see if I'm online in the Wi-Fi. So just wanted to see if I can quickly give you a decode of that ADSB. I consistently have problems associating with the Wi-Fi. So yes, serious all the time. So yeah, you can see there again. It's gone. So it cannot associate. So I cannot go online now to look for a decoder for the ADSB. Yeah, so maybe a few more words before we go into more questions in what kind of software is included or what you can do with it. One interesting tool is called RTL TCP. So it's basically a small server, so you can use an old laptop or an embedded system from Olimex or from any other vendor, of course. You can attach the radio to it, and you can run this RTL TCP on it. And then from a remote computer over the network, you can connect to the RTL TCP and obtain the samples over the network. So this way, it's easy to put a device outside with a better antenna or something like that, and run Ethernet inside and have a good reception. Because if you have long coaxial cables, they have lots of losses, or the cables have to be very thick and sort of not very easy to install and so on. But putting the receiver directly at the antenna and then forwarding digital samples over Ethernet is, of course, a very nice solution to this problem of directly capturing at the source and avoiding any antenna cable losses. Questions?
Are there any cheap ways to broadcast? This is a very cheap way to listen, but what if you want to broadcast?
Well, for transmission, unfortunately, there is no really cheap device available right now, that I'm aware of, at least. That's a little bit harder. One of the most exciting devices that have been released recently is called HackRF, which is another hardware for software-defined radio. Attaches over USB to your computer. There's actually one here. I've seen some people playing with that in the team room. The problem with this device is that you can basically only pre-order it, and it will ship at some point next year because they have so many orders that they're a little bit overloaded. Otherwise, of course, there's the USRP family of devices which are available, which can transmit. And you can use those devices, for example, with some other GNU radio-based software to transmit, well, of course, analog radio. It's very easy, but there's even code for transmitting DAB, the digital audio signal, for example, or there's code to transmit even a GSM network. With OpenBTS, you can run your own base station on such a software-defined radio transmitter. However, as soon as you get into transmitting, keep the legal situation in mind. Be careful. I'm not sure what's the situation regarding listening into clear text signals in Bulgaria, but that's normally less problematic. But as soon as you start transmitting, you have to know what you're doing, where you transmit, and make sure that you have permission to actually transmit on those frequencies. Okay. More questions?
Question.
Yes, Victor.
Yes, I think thanks first. Any practical ways to hunt for something hidden in the spectrum? For example, I remember maybe a year ago, Finnish researcher found and managed to hack the displays for the public transports with USRP.
Yeah, I mean, that's not really hidden. When you say signals hidden in the spectrum, then I think this makes me think of like, you know, some kind of bug which is hidden in a room somewhere and which does some, you know, basically for surveillance or something like that. That's what I would consider hidden. But
well, then let's say unexpected, maybe interesting signals.
Okay. Well, the displays for public transport, I would say they are very much expected. So there's many technologies. I mean, the displays at bus stations and so on, that's a very classic one. In Berlin, for example, we have even video screen displays inside the subways. And they get the data that gets displayed, basically, you can say it's like a slide set of a presentation program or something, that gets also transmitted over DAB in the stations. So there's a DAB transmitter in the subway stations that sends the most recent data to a server inside the train cars, and then they display it all the time. So there, in this area, you can find a lot. Even in Berlin, for example, we have a system where buses, when they are close to certain intersections, they get a green light because the system knows a bus is approaching. So already, I think more than 10 years ago in the CCC magazine, there was a description how that signal is, it's a BPSK signal and how it looks like and so on. So basically to send this information to the traffic light that a bus is approaching now. And there are many of these systems when you start looking. Lots of fun. People have had lots of fun with RFID systems, which are, well, by their very nature, are radio-based. Also with SDR receivers, you can also look into, well, some people call it tempest, or basically radiation from devices which is not intended. I'm not sure if you have followed the, how can I say, the history of voting machines in the Netherlands, where basically you could, I mean, okay, so generally all electronic devices transmit some signals, which are not intentional. It's just by their very nature, there is currents are moving inside circuits, and those currents create electromagnetic fields around them. Now the question is, how well are they suppressed or not? And quite often, based on the information that you receive, you can conclude what might be happening in the device. And in this particular case of the Dutch voting machines, you could detect for which party somebody was voting at the point he was making his vote, because basically it depended on the characters in the LCD display what kind of signals you were receiving from that. And after some calibration, people could actually say, yeah, that guy is now voting for this. From outside, in front of the building of the election office, they could basically say, oh, this guy has voted like this or that now. So there's all kinds of things once you start to explore radio signals that you can find, and it's a very fun thing to do. What we also have in Berlin, for example, my hometown, is all the local trains, the S-Bahn that drives around as public transport, not the subway, but we call it S-Bahn. They have a transmitter that transmits their current GPS position all the time, unencrypted over a VHF radio. So basically, by tapping into that, you can basically have a live map of which train is where right now, which is quite funny. Well, there are all these interesting applications. There's also a Vattenfall, which is a Swedish electricity utility company. They operate the Berlin power grid. And they have their own unencrypted Tetra network. So I haven't really seen much activity on that network, but you can find some press releases that they were using this for remote controlling switch in a power station or something like that. And we think about this, this is unencrypted and unauthenticated, that might not be the best idea. So then a reporter got to the electricity company and told them, you know, what about this? And he said, oh yes, but that's illegal. Yeah, it's like, oh yes, this is illegal, so why would anyone ever do that? That's maybe a very German response, I'm not sure, but in any case, you find lots of systems. Also now, when you think of smart meters, for example, or I'm not sure how it is here, but in Germany, when you live in an apartment, quite often the companies renting these apartments, they now put electronic meters at each and every of your heaters in the room, and then there's basically a central device in the building which picks up all the usage information, like who has used how much of the heating, and then it transmits that over GPRS further. And this local link between the central node in the building and the actual heater in your room, that's most often unencrypted, so you can tap into that. Also, you have, of course, all the electronic remote controls for garage doors and all kinds of things that people do over radio. All the remote-controlled light switches that people find convenience in their home. They're not encrypted in any way. You can try all the codes, and at some point your neighbor's light will go on. So there are lots of radio things that people don't really think a lot about before they use it. Also, in some countries, analog 2.4 gigahertz video transmission for putting a surveillance camera somewhere is used quite a lot. Or for, let's say, a video phone for your baby or something like that, that works wireless. Quite often they use analog video, and then your entire neighborhood can watch your baby. That's, well, if that's what you want. Well, I'm not saying anyone wants to do that, but it's just that a lot of people are not even aware that they're doing this, that they're broadcasting this signal to lots of other people. Huh? Okay, so yeah, lots and lots and lots of interesting signals out there. Yeah.
Just a final question. Considering what you just said about all the radio transmission happening right now, and what we know about the upcoming wave of Internet of Things embedded devices, can you give an example of properly implemented in terms of security application of such system, and if it was based on software-defined radio? I mean, would you share your experience in this area? Because obviously a lot of things are not done right because everyone believed that it's going to be illegal to break something, and we all know that this may not stop someone from doing so.
Yeah, well, I'm not really the right person to respond to that question. I don't really do much work in the area of Internet of Things. I can say a couple of comments. One is regarding software-defined radio in that area. Most likely you will not find much software-defined radio. In a sense, this fully reconfigurable, everything runs in regular software. Because power consumption is a key aspect of Internet of Things, and you can always have much less power consumption with a hardwired implementation of a radio system as opposed to running it on a general purpose CPU with software. You consume maybe 100 times more power than you need for achieving the same goal. So it's basically, the more you go into the true SDR field, the more flexible you are, but then also the more power you need. On the other spectrum, end of the spectrum, you have low power devices that can be highly efficient, but then you don't have this flexibility anymore. And regarding security, yes, I see, I don't know how many nightmares that are coming up. I mean, we already had so many historic problems with insecure systems. So for example, these aircraft transponders don't believe there's any authentication inside. Multiple people have already demonstrated at security conferences that you can basically make airplanes appear on all kinds of systems that don't exist just by spoofing those messages. The same goes for AIS with ships and so on. So all of these systems that are deployed, apparently nobody ever thinks about security seriously in any way. And then, with regard to the ships, the vessels, now there's regulation that whoever manufactures such a transmitter must make the vessel identity, you can only program it once and then no longer. I mean, what kind of stupid regulation is that? If your implementation is software, in particular if it's free software, of course you can change the identification that you broadcast. So it's, trying to mandate capabilities of hardware is clearly not a solution. Well, we'll see what the future will bring. One other interesting system that you can listen into, you need a satellite dish for this though, is the Thuraya satellite telephony system. So there's an Osmocom project called Osmocom GMR by which you can receive the satellite communication. And the encryption has been broken for several years. The voice codec has been reverse engineered. And the interesting part about Thuraya satellite phones is that by the protocol specification, every phone that makes a call must transmit its complete GPS position at the point you attempt to make the call. So the call cannot be made unless you include the full GPS position of the phone. And that's completely unencrypted, and that gets rebroadcasted, so it gets sent up to the satellite, but then the satellite is broadcasting it with a lot of power down in the downlink again. So basically, it's, and commercial companies have been doing this for many years, sell-to-sell systems to military and intelligence agencies. Basically, it's a satellite antenna with SDR and the respective software, and it draws you a map where you can see, well, here on this planet, somebody's calling that and that number right now. It's so funny when you start to look in these things. I once called it the let's shoot Gaddafi feature in the satellite telephony because I cannot think of any other legitimate use case at all why a system would have such properties. It's really only for military and intelligence agencies in there. There's no other reason. It's not required for technical functionality. Okay, let me stop there. Thanks for your attention. I'm not sure if you, yeah, okay.